In this example, we were given the series 1 minus 1 half x minus 2 plus 1/4 x minus 2 squared, so on and so forth, with the nth term being negative 1 half to the n, x minus 2 to the n, plus, and this series continues forever. So if you recall back to our role with geometric series, we saw that in a geometric series, the form it had was a plus ar plus ar squared plus dot 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 plus a to the r to the n minus 1 plus so on and so forth. And that eventually came to the form of n equals 1 to infinity of a r to the n minus 1. Okay, so if you look at this form and you look at the form of the power series, which we gave in the beginning of the notes, power series looked like the power series looked like C0 plus C1 x minus a plus C2 x minus a squared plus dot 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 plus c to the n x to the a x minus a to the n plus dot dot dot. And this final form equaled the series from n equals 0 to infinity c to the n x to the n. Okay, so if we kind of compare, you can see that these two, if we equate coefficients, right, based on the powers of x, you can see that the r here, well, if the r is equal to this x minus a thing, right, and the c1, c0, c2, if there's some relationship with a constant multiple a, then these two series are equivalent, okay? So if you look at each of these values in this series, the indexing here is also important to note that this n goes from 1 to infinity, whereas this one starts at 0. So imagine if we rewrote this series as a situation in which the indexes were to match, could we finagle an equivalent relationship, an equivalent connection between them? Okay, and so that's kind of the idea that we're trying to match out. We're trying to see if we can express this and finagle it from a power series form, matching it with the geometric form so that we can identify and possibly then simplify. Okay, so let's look at this value as if it were a something of the form. Let's see. Okay, so let's equate and look to see. So what if we identify that C0 here is equal to 1, C1 is equal to negative 1 half, C2 is 1/4, and we can go out to Cn being equal to negative 1 half to the nth power. Okay, then you can see that from this relationship, A is equal to the 2 that you see here. So we're identifying A equals 2. Now, be careful. This A here is coming from this sequence, okay? So it's this A, not the coefficient, not the common ratio here that we're pulling out from the geometric. We're going to try to make it look like this form, but the common ratio, the common constant A term here is not the same A as the where we're being centered at for the series. So this A is in reference to the power series. We're trying to make this power series into a form of a geometric series. Okay. All right. And then we look, C0 is equal to 1. We get that from here. C1 is equal to, looks like negative 1 half. C2 is equal to 1/4. Notice the alternating signs. Okay, and this goes out to C to the n, which was, we saw, negative 1 half to the nth power. Okay. So the ratio then, to identify the ratio, look at what each value here we have this thing. This is where the r's need to line up, right? This needs to match this. This needs to match this. Oh, sorry, no, that needs to match that, and that needs to match this. Okay, so the ratio then is that we're going to have an extra 1/2 left over. That would be the value that we're factoring out. So the ratio R is going to equal negative x minus 2 over 2. And that implies then, that this series will converge for the absolute value of x minus 2 over 2 negative being less than 1. Okay, so if the negative in the absolute value can be absorbed, so we can just write this as, so this will first become just absolute value of x minus 2 over 2 less than 1. And then if we open up this, if we open up the if we open up the expected values here, or not the expected values, the inequality here, we get negative 1 is less than x minus 2 over 2 is less than 1. Okay, so that's just opening up the absolute value, this absolute value. Then I'm going to multiply everything through by 2. Since 2 is a positive number, it's not going to change the direction of the inequality. Okay, and so there we go. And then finally, to solve for x, I'm just going to add 2 to each of these points. So negative 2 plus 2 is going to give me 0 less than x less than, and then 2 plus 2 is going to give me 4. So here is the radius of convergence. Okay, it's the radius of convergence there. And we can then utilize the exact value of the sum, since we know that a is 1. A in the formula of a geometric series has 1 over 1 minus r. That's the infinite series value. We're going to have 1 minus, and then we have our ratio, which is negative x minus. It would be an x plus 2 if I bring that that negative upstairs right here. So it becomes a negative x, it becomes a positive 2 over 2. Okay. And if I factor that negative back out, that makes that up into a plus. So I can rewrite this simply as 1 over 1 plus x minus 2, switching the signs back, and then getting a common denominator. So this is going to change that to 2 over 2. Then this is going to be x, or 2 plus x minus 2. So those are going to cancel. The 2 here minus 2 is going to cancel. And then this is going to be, I can simplify this as 1 over x over 2. So this is 1 over the reciprocal. This is just simplified as 2 over x. Okay. So this really interesting and complicated integral or integral series has a closed form of x 2 over x, which is really, really cool. And we can therefore rewrite this entire series then as 2 over x is equal to 1 minus 1/2 x minus 2 plus dot dot dot, as we saw up above, with the radius of convergence from 0 less than x less than or equal to 4. Okay, so we found a new series and transformed it into, or found a closed form for the series. In other words, we found that f of x is 2 over x has a series expansion, an infinite series, or a power series expansion of 1 minus 1/2 x minus 2 plus dot 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 all the way out for infinity, with a radius of convergence of 0 to 4. All right, I hope that was helpful, and I'll see you in the next video.